Hello, hello, hello. Count here, back with another Unity coding a graph theory shortest path solver. Anyway, in this episode, we are going to be, doing some things. The first thing I realize is that I probably need to plug in my laptop because I don't want my battery dying. The next thing is that I actually probably should have added these these other two commands to our system here. So let me go ahead and actually put that in our good old, where is it? The extras, the commands list. Under the commands list, we need to do a bit more editing, and well, hopefully it's not going to, hopefully we don't have to add too much, but we have the delta, and okay, we have to do a bit of editing. So it's not just that. So number over here, we're going to have to replace this with the deleteEdge, and then we have to do the name, deletes a given edge. Name is equal to the name of the edge to be deleted. And then number 4 is the deleteVertex. Again, we're going to have the name and deletes a given vertex. Name is equal to the name of the vertex to be deleted. All right. With that, we have to do a bit of modifications now to the numbering. So this is 5. I'm going to have to look at the side. So this is going to be 6, 7, 8, 9. This one will be, the next one will be 10, then 11, plus 2, 12, 13, 14. Okay, and that's it. Okay, now we actually need to have the code work. Now the code actually needs to be done. So let me go ahead and do that. Where is it? The miscellaneous and the player command prompt is our script. Let me just make sure the stream is public. Yeah, it's public. Okay, so we have quite a lot of stuff. These are not in alphabetical order. So next is we have Next we have delete edge, which will be we're going to take in the name. We also have delete vertex name. Now here we're going to have a private void. Oh, first off, we probably need to do under our execute name. We actually need to add a new case. So case delete vertex, and then we'll return then case delete edge, and we'll do something. This one looks like something that would close the command prompt. So yeah, we'll go ahead and do that. Close the command prompt, and then we'll leave a space for our function. So this one is the private void delete vertex. And we have to put the string, input it cmd, and of course we need to build the name. So we're going to have a string vertex name. We're going to have it equal to this. Then of course we need a boolean called build string. What did I call it? Make string or whatever. And I think I'm switching it around now. So make string, and then this will be equal to false. What else is there? I guess that's really it. So of course we have to do our for each loop now, which for each character is that how I do it? No, yeah, it is. In inputted CMD. So we have to do our if make string is equal to true, then we have to do else. If the character is equal to this thing, then make string will be set to true. I believe that's how I did it. All right, and well, yeah, first off, what we have to do here is if the character is equal to this thing, then we're just going to break. Else, what we can do is do vertex name plus equals character. Now, what we now need to do is do our, again, we have to do this. Let's do this, and well, this is the first one that we need to do. You have to check, hey, is there an actual, did you actually close off your brackets? And then here, what we have to do now is we have to check for certain, we have to check for something. Okay, what is that something though? That something most likely is going to be the length of the vertex name. So if vertex name dot length, not last index of, dot length is less than or equal to 0 somehow. I'm pretty sure that's how I do it. Let me look at something that's yeah, I guess we could. If this is less than or equal to this, we obviously have to do our notification.notify, so, and we also have to return. So, however, I do want to make sure that the naming thing is actually like very, if it's must give a vertex name. Hold on a second. Let me look at this edit vertex. The new vertex name. And oh, okay. Yeah, there we go. And then under that, we obviously need to check if the vertex actually exists. So here at car. Anyway, we had to check if graph editor.script vertices contains value, contains key. We pass in the vertex. I don't want to call it vertex name. I want to call it the delete vertex name. We're going to call it that. Delete vertex name. If this is equal to false, then we are obviously going to have to return. And I'm going to once again refer to this thing to make sure that I have a uniform, a sort of uniform kind of thing. So if we could not find the vertex, yeah, so on. Could not find the vertex. And this one is going to be the delete vertex name. Now, if we can find it, what we have to do now, hold on, is that really it? Is that all the conditions? Really? Is that all of the conditions for this script? So we have the name, and we have to say, hey, you have to close off your brackets. You have to make sure that okay. So if we do this, okay, then, okay, actually what we need to do now is, I need to look at a reference to the graph editor to see how we delete a vertex. When we delete a vertex, oh, we pass in a string. Oh, that's very interesting. So we actually don't need to, like, you know, what is it? We don't need to specifically get the vertex. So we're going to do graph editor.script.delete vertex, and we pass in the delete vertex name. And that's really it. Wow. Graph editor is also this. Is it the same thing for deleteEdge? All right, it is. That's very interesting. Okay, so now we have to do the same thing for, or we're gonna put it here first. For the delete vertex, we now have to call delete vertex, and we have to put CMD code, obviously. So yeah, and then we have here, this is going to be deleteEdge, very basic CMD code like that, and I don't care if it doesn't exist because it's going to exist in a few seconds. So a private void deleteEdge, and then we're going to have a string called inputted CMD. We obviously have to do the same exact thing, so we have the string, which is going to be deleteEdge name, and of course we have to set it to this. And then we have a boolean, which is obviously make string, and this is going to be set to false by default. Then we have to do a for each loop. So yeah, here we have a delete. We have for each character, we're going to have call it, not that, we're going to call it character in inputted CMD. As always, if make string is equal to true, we have to do our else. If the character is equal to this guy, we have to make string is set equal to true. And now what we have to do is again check if the character is equal to this thing that we're going to break. Then what we have to do is delete edge name plus equals the character. There we go. Now, of course, we're going to have to copy this guy and put it right here. Put it right there. And I'm going to refer to the edit edge for the other two. So the other we're basically going to copy paste these, because let's face it, it's basically the same thing. Script is honestly very repetitive. The only thing is that we just need to replace the edge name with delete edge name like this. Delete edge name, and lastly delete edge name. So yeah, that took care of those two right away. And of course, all we need to do now is to graph editor.script.deleteEdge, and we pass in the delete edge name like that. And hopefully, hold on a second. Let me make sure that when we under graph build this is the graph builder. Under the graph editor, if we delete a vertex, we are not notified. Okay, so that's probably something I should notify. I should probably notify the player that, hey, we deleted a vertex. So we're going to do notification.notify deleted and we're just going to have that go for about 0.75 seconds. And then here we're going to do the same thing, but for the edge. So here, this is going to be delete edge name edge. I'm just going to do it like that. Then do the same thing for a good old vertex. All right, with that, hopefully now the thing will work. I mean, I hope it does. So let's go ahead and test it out. So if I was to, let me go ahead and make a graph very quickly right here. And under this, let me go ahead and go back to view mode. So this is, name is A, this one is that one, so it's A00. All right, so AA0. So let's go ahead and Control Enter. Then we'll go ahead and open that up. So deleteEdge, and we're going to pass in A0 like this. All right, then we can try and do the deleteVertex, and we're going to pass in A0. All right, it works. So yeah, that definitely works. So now what we need to do here, now after we've done those two, we actually need to work on the algorithm for finding the shortest paths, possibly paths. Because this is the part where I have a feeling I'm going to be struggling a lot. I'm actually fairly surprised that I didn't struggle that too much. However, this is the part where I believe I'm going to actually have a hard time. I'm not sure how I'm going to do, but if anything, it's definitely going to be the most difficult. I'm not sure if I should have Dijkstra's algorithm in a completely different script as well, because it might be just that complicated. So I guess I might as well do that. I might as well do that. Yeah, I'm gonna put this one is going to be. I don't know how to spell the name. Let me go ahead and delete that new behavior script, because that's not actually how we want to call it. I can never remember. It's hard to remember how to remember the name. Yeah, remembering the name of the algorithm is a bit difficult. So, in honor of Dijkstra, I'm gonna put DJ. Come on. Dijkstra algorithm. Did I spell it right? Yeah, I'm just gonna do it like that. And well, yeah, this is going to be our good old algorithm. I'm not sure if I should put this with mono behavior, because I don't believe I need to have it with mono behavior. But I might as well. I'm just gonna keep it anyway. So yeah. So first off, the algorithm. This thing is probably going to need a reference to the path solver. Under the path solver, actually we're probably going to need a public static, or I don't know. It is most likely, I believe actually most likely, if we are going to have if we're going to put Dijkstra's algorithm anywhere, it is most likely just going to be, where is it? Under the graph space. Because we have the graph editor, we got the graph builder, and we got the graph solver. We might as well put the algorithm there as well. So we're going to actually make a reference to this. So we have a public Dijkstra's algorithm. We're going to call it Dijkstra. So we're going to do Dijkstra is equal to get component game object dot get component. There we go. Actually, I think it's still get component is fine. We just need to do Dijkstra's algorithm like that. Now we don't really know what we're going to use it for yet. Although we do need to know that when we call this, we're going to have a public function. Actually, this is so complicated. My brain can't handle it. Oh gosh. The first thing that okay, I'm not sure if I should call this Dijkstra's algorithm, because technically this, I don't believe I'm just going to put Dijkstra's algorithm here, but I will probably have Dijkstra's algorithm just write a public void yeah. But if anything, I'll go ahead and just call this the solver algorithm instead. and this one is going to be called Dijkstra. Dijkstra. I'm gonna call it that. And now we're gonna now have to place this one with solver algorithm, like so. Solver algorithm. And of course we have to make sure to rename this. So instead we have to call this solver algorithm. And well, under the solver algorithm, what we have to do here is public boolean existing solution, not particle collision event. Okay. So what this basically does, it has a, we take in a, okay, let me just look at these. We have a vertex. This is going to be start vertex, and we have another vertex, which is going to be the end vertex. It basically, what this does is checks for if a solution does exist between the two vertices. Or should I? I'm not sure if I should actually just combine this with Dijkstra's algorithm, because in a sense I'm technically doing this. So I'm not sure. Okay, let me look at the vertex. So the minimum distance is actually it's already a float. Under a utility, I'm going to actually going to do this. I'm going to have a public static float, and this one is get minimum value. In a sense, all we need to do is to pass in an array of floats called about the check values. And we have to do for each. So first off, we need to have the min value. This is going to be set equal to check values 0 by default. However, for each float value in check values, if the min value is if value is less than min value, then what we have to do here is to take min value and set that equal to value. And once we do that, we just have to return min value. So yeah, this is something we're going to be using. We could do the maximum, but obviously I don't believe we're going to be needing that. Do I actually necessarily need that? Can I just use a list of a list? So I could do using system.collections.generic like this. And then over here we'll have a list of float. And well, it's going to be exactly the same. Under the solver algorithm, I'm pretty certain that we're going to be using a system.collections.generic. Now, this is the hardest part. This is where I'm going to be struggling a lot, because I still have yet to figure out how this is going to work. the actual algorithm, I'm not sure if I want to have this existing solution, because then again, I think that Dijkstra's algorithm can technically solve for it. Okay. I guess the first thing that we need to do is have a list of vertex, which is this. We're going to call this we're going to call it graph vertices, and this is going to be equal to graph editor.script list. Wait a minute, is that a private boolean? Oh, it's a private thing. Okay. Well, oh, it's the vertex names. Yeah, we're not going to do that. We're going to actually make a public list of vertex, and we're going to be list vertices. And well, all we need to do is to make a list of vertex. This one is going to be the vertices, and this is going to be equal to a new list of vertex, obviously. Then under this, we have to do for each vertex in vertices dot values. Let me check my mic. So yep, it is dot values. If, oh no, we don't do if. What we do is the vertices dot add vertex, and then we return the vertices. We're gonna have to. I'm not sure if we're gonna have to. I don't believe we need to do the same thing with. I don't believe we need to do the same thing with our good old friend the edges, but this one makes a list of all the vertices. All right, and under our solver algorithm, we need to do .script.list vertices. And with that, well, the first thing that we need to do, how I believe that we need to do this, okay, let me list out the fun things that happen in Dijkstra's algorithm. First off, we pick a vertex. Let me plug in something. And I'm going to go to Paint Tool Sci that. Let me go ahead and open a new. And under this, let's go ahead and make some sort of graph. This red, let me just make a very simple graph. So we're going to make a rather simple graph. However, there's going to be a bit of a catch. We're going to do this, and we actually technically are going to do this. So first off, we're gonna make it a very simple graph. Let's say this is A. Let's say this is A. We're gonna call this one B. We're gonna call this one C, D, E. Now, first off, let's say we want to find the solution between. Let's say we want to go from A to C. Now, obviously, this is a bit easy this is going to be easy for you to say, hey, obviously there's only one path to it. But for the computer, we actually have to do something different. We actually need to say, if we want to go from A, we're probably going to have to start from here. And let's say that this value is 2, and this one is 1. What it's going to have to say is, we're going to start from A and then branch out to whatever edges that are connected to it. And whatever vertices that they touch, it goes to that one. So this one's going to be number 2. And then, well, there's only one edge here. But what I'm trying to say here is, like, let's say that there's this other edge right here. Let's say that this one is a 4. Now, you might say that, hey, that doesn't, so technically what the algorithm will do is say, let's start here. This one is actually going to be a 0, and this one's going to be a permanent. And technically, what this will do, we'll go across these edges that are directly connected with A, and then here under E, it will say, wait a minute. So the distance from A to E, the minimum distance is currently, as of now, is going to be temporarily 2. However, for C, it's going to be temporarily 4. Now you might be saying, wait a minute, what about this one? This is definitely not the shortest path. But wait, hold on a second. We're not yet there. Because technically, once we do that, we have to go get the smallest value. We need to check for the smallest value. We need to check for the smallest value. And we need to get the vertex with the current smallest, shortest path. And then so now that we know that, hey, E is now the shortest one. So we're going to now set this to a permanent, and then we're going to go ahead and go to here. And since this is now going to be a distance of 2 plus 1, which is now 3, we can go ahead and say, wait a minute, this is not the shortest path, it's now this. And then, well, now again we have to get the smallest one, and oh hey, and now we can say, oh hey, this one is the shortest one, so it is going to be the permanent. So 3p. So this is our final answer for our good old buddy here. Now this is actually a very simple graph. This is a very simple graph. It's literally just 2 paths. However, it can be a lot more difficult because technically there could be a whole intertwined network of vertices connected to this. I just simplified it so I can draw it quickly. But again, like, look at my thumbnail. That one is a lot more complicated. On the thumbnail of the shortest path solver, as you can see, if we can actually add like a ton more of vertices, and we can interconnect it like way much more connected, like so. And yeah, as you can definitely see, things start to get a little complicated here. So like, if we want to find the shortest distance from here to, let's say, this guy here, it's going to be a lot more complicated because now we have to go start from here, then we have to go branch out to here. Then after we do that, we have to branch out to here, and then we have to go back here. Or it depends on which one is the next smallest one. If this is the smallest one, we're going to have to branch out to all of these other vertices. And this is the thing that is kind of confusing me. I'm not sure how to have the computer remember what the shortest path is. This is my issue. How do I have the computer remember that, hey, this is the shortest path? Because yeah, I can get the distance, but I want to show the path. I don't want to just say, hey, this is how far away, this is the minimum distance. Because the minimum distance doesn't mean anything if you don't have a path to it. So yeah, that's one of my issues that I'm trying to figure out how to do. And let me go ahead and close out Paint Tool Sign now. No, I don't want to save. No, I don't want to save. All right. So with that, I hope you enjoyed my lecture on Dijkstra's algorithm. It probably made no sense, but okay. So what we have to do is pick a vertex, then check all connected edges. Then what we have to do here, I also wanted to make a list of vertex. Wait, I'm so difficult. I'm having such a hard time understanding how to do this. Now I'm wondering if I should make a dictionary of vertices and floats. Because technically, we can technically associate, but that would be useless because the vertex already has a. The vertex already has a given minimum distance variable in it. So what we have to do is pick a vertex, which is going to be the starting vertex. check all connected edges, and then we have to do is get the minimum distance to the other vertices. Then after that, we have to do, when we get the minimum distance, we then have to get the vertex with the smallest distance. Then again, we have to check all connected edges. And we have to, oh wait, I also forgot to get the vertices, the vertices on the other side of those edges. And okay, and then we have to repeat in a sense. So here's the thing: we can't use a while loop. The problem if we do a while loop is that, well, if we do a while loop, we're end up going to have Unity do the thing where it just freezes and it doesn't know what to do anymore. Because not all vertices may be connected with each other. As I've shown in the drawing, you can have a disconnected graph where there are parts of the graph that are inaccessible at all to other parts of you have a graph and then there's some parts that are not accessible. So in a sense, what I'm going to do is I have to do something to. This is why I have to check. This is why I'm not sure if I'm. This is where I'm having a bit of difficulty. Like, how do I do this? I know how the algorithm works. I can do it in my head, but how can I make the computer do it? The computer is actually a lot more difficult to do because, well, we need to teach it to recognize that, hey, that there is a connection between these two vertices. There's a connection between, so on and so on. And well, one thing that I would like to do here is under the graph verticer, I want to actually make another miscellaneous function, and that is actually, no, we're not going to do it here because I think that it probably would be better to do this, a private void. This one is get connected edges. So actually this one should be a list. This one should actually be a list of edges of edge. A list of edge, get connected edges. Then we have to do is grab a vertex. So then we're going to call this the check vertex check for edges. We're going to give it a long name because why not? So here what we have to do now is we have to check if the vertex exists. So if graph editor.script.vertices contains value, I'm going to pass in vertex check for edges is equal to false. We're going to want to return because it doesn't exist. And this one's just going to be a debug.log warning vertex check for edges.gameObject.name does not exist, is not in the vertices dictionary. There we go. Return null. All right, so what we have to do now is technically if we don't actually need to do we actually don't need the graph editor script thing to check if there are connected edges to it because technically this thing will kind of do it for us already. What we have to do now is to go for each edge, found edge in graph editor.script.edges.values. What we have to do now is if found edge dot okay. Okay, if found edge dot p1 dot p okay, if found edge dot p1 is equal to vertex check for edges, or found edge dot p2 is equal to vertex check for edges, then we're going to have to do is we have to make a list of edges, edge connected. We're just going to call it connected and equal to this, a new list of edge, obviously. And connected dot add, well, we're going to found edge. And I'm pretty sure that I made something similar to this on our graph editor. Yeah, exactly. Very similar to our. And then at the end of this, we're going to return a return connected. Now, on the pick our vertex, we have to do here. Wait a minute, I'm kind of curious now. Okay, never mind. Okay, we can't do that. Because I'm trying to figure out how to make the thing know that there is this. I'm trying to figure out how to let this thing know when to stop. When will it stop? Because how do we do this? Okay, now what we need to do, what we actually need to do here is to actually have to do a for each loop here. Actually, now I think about it, let's go ahead and get rid of this. Under our solver algorithm, let's go ahead and get rid of that as well. And here this one will just be equal to a new list of vertex. We're going to go ahead, put this up here, and what we do here is for each vertex, found vertex in graph editor.script.vertices.values. What we have to do first is found vertex.state vState is equal to a vertex state.temporary. That's exactly what that means. And then what we have to do is graph vertices.add found vertex. And then now what this will do is just basically give us the list of all the vertices. Again, I'm trying to figure out how to code this. This is giving me a hard time figuring it out because I can see I can see a while loop, but then if I do a while loop, that would make disconnected graphs a problem. That's what I'm having a hard time figuring out. Because not all vertices can be set to a permanent state. Let's see. So the first thing, I'm trying to figure out, how do I do this? Okay, we have a vertex. Then under this vertex, what this vertex is going to be the path solver dot script dot. It's not going to be Dijkstra. It's path solver. It's a public vertex points. Vertex points 0. Okay, what we have to do here, we pick a vertex, and we want to set one thing that we want to do, and we want to do dot min distance is going to be equal to 0. This is our starting point. And then what we have to do here from then on out is do, again, path solver dot script dot vertex points 0 dot. Okay, I think we also would like to have a function here, which is going to be a private void set vertex values? I'm not sure. Okay, but if anything, we're going to have is vertex one. We're going to have a float, which is going to be the distance, calculated distance. Why not? We're going to make it, and then this one is going to be the new state. First off, we need to actually make sure if calculated distance is less than or equal to, is less than the min than the set vertex values. We also need to pass in the vertex, which is the edit vertex value, edit vertex values dot min distance, then edit vertex values dot min distance is going to be set equal to calculated distance. Now I'm not sure if that just made this thing completely useless, but whatever. All right. Then what we have to do now is do edit vertex values dot state vState is equal to the new state. So in a sense, what we have to do here is do set vertex values. Then we have to do path solver dot script dot vertex points 0. So we pass in a 0, and this one is going to be vertex state dot permanent, because yeah, that's how it's going to work. So let me also make sure. Hold on a second. Wait. There's also another thing there's a Boolean that I actually, and that is get distance I don't know. Okay. We also have to, okay, I'm going to go back to my solver algorithm. We also need to make sure that this is true, and we also need to make sure that the vertex state, okay, if the vertex state is permanent, then we're going to actually just need to return because it doesn't actually do anything. If edit vertex values dot vState is equal to vertex state dot permanent, we just want to return because there's no use to it because the state is permanent. We can't actually edit it. Okay. I completely have no idea what this Boolean is anymore. I think I had an idea what it would be before, but I don't think I know what it is anymore. So wait a minute. Wait. I think I wait, no. I think I realize what this function is for. I think I realize what this thing is for now. So what we have to do here is under the path solver, but first we also need to make sure we have to also say or vertex values state values dot, actually no. That's only useful for the ones that are this. If we do this, then we actually then what we can do is actually if we enter vertex values dot, what is that Boolean called? Get distance. It's going to be set to true in this case. Otherwise, we have to do this. Actually, that's another thing that we need to do. We actually need to do found vertex dot get distance. Is this the Boolean? We'll be setting this to false for all of them. Something to make sure. Something to make sure of. Because we only want to check because of this one to get the minimum distance of the other vertices. But we can technically this is so hard. I'm trying to figure out how this works. I cannot do a while loop. But here's my problem. I cannot do a while loop. I can't do a while loop for the one thing that's making me confused is like we can't do a while there is, I can't do like something like while there are vertices with a temporary state. Yeah, I cannot do that because technically this will not work for anything for disconnected graphs. This does not work for disconnected graphs. Otherwise my computer would just completely explode or something. Which I guess is probably why I need the existing solution to exist in the first place. So I guess I might as well check if existing, okay, we need to put this back to existence. I guess that's why I need this. So if existing solution between our path solver script dot vertex points 0, and we do path solver dot script dot vertex points 1 is equal to false. You know what? Needs. I believe I'm just going to do this. Wait start. We're going to have a private reference to our graph editor, which is going to be gedit, and then we have a private path solver, which is called path solve, and gedit is equal to graph editor.script. Then path solve is equal to path solver.script. Now it's going to be path solve, then gedit, path solve here again. Yay, okay. I could be extra careful and say and check if this vertex exists, but I'll be honest with you, I'm too lazy to do that. Even though it's like just enough. If gedit, not get gedit dot vertices, come on, vertices dot contains value, edit vertex values is equal to false. We're going to return, and we're going to do a debug.log warning like that. Could not find vertex like that. We're just going to go ahead and collapse those so that way it's a lot more neat. And well, yeah. So existing solution. So if there's an existing solution between these two vertices, if this is false, then we're going to have to return, and we're going to actually have to choose notify player that there is no solution. No solution state there is no solution. All right, so with that, okay. This is in a sense a smaller version of Dijkstra's algorithm. Let me go ahead and check something. Okay, sorry, I was looking at something. What the heck how am I supposed to do this? How am I supposed to do this? How am I supposed to do this? I think I might need to go back to our Paint Tool Sci app right here. We need to go back to the drawing board. Okay, this is not a board. But seriously though, how the heck am I supposed to do this? Let me just draw a random graph again, so that way I can do stuff. Say, we're not starting off with red. Let's just draw some very definitely artistic graph that's totally, yeah, okay. And then let's say that this is connected with, that all this stuff is interconnected in some weird way like that. And then we have this graph over here. And let's say we want to go from this graph, let's get that. Let's say we want to go from this graph to this one. How will the algorithm actually detect that? For us, it's easy. You can say, obviously this one is connected and this one is disconnected, but how do we get the computer to tell that without crashing it or something? My only other way is to say, hey, we can go along this, if this, for some odd reason, if it's not like this, if we can go across this vertex and say, hey, this guy, we can go to here, and then we can get the other two vertices, and then, so this is going to be go across the other two vertices. Then with that, we can go ahead and go here. It's actually a cycle here. I just noticed that there's actually a cycle. And this guy, so I'm actually going to name all these edges just to test something. Okay, so we're gonna have like a list. We're gonna have a list of, here we can have a list of edges. So we're gonna have that over here, and these are the ones that are crossed, the ones that we already crossed. So on the first one, we're going to label this as 1. We cross over A. Now, if we go back to then under our second one, we actually go over 2 edges. We go from here to here, which is going to be B, B, and the other one is E. And the next one, in the next iteration, so these are all the ones that are crossed. We go from here to here, go from here to here. Now we don't want to go backwards, which is why we have this crossed edge thing. So now we have C, and then we have D. And then our last, I believe it's our last one, there's 4. You go back from F. You go to F. Now, technically there are more edges, so we can take this E, F, G, I, H, like this. And well, technically, we have not crossed. These are the only ones that we can go to because they are not connected. And what we have to do here now is to say, well, what we have to say is G, H, I didn't, forgive my terrible handwriting, I'm trying to write this quickly, didn't get crossed. Therefore, there is no solution. Now let me go ahead and fix my ugly, terrible handwriting. Wait a second. No, this is still not going to work. I just realized, even if I just realized I could even check if there is no solution. I could check as many things as I want. I can do as many checks. I can check for if there is a no solution or not. It still doesn't matter. These vertices are still going to have a temporary, they're still going to have a temporary thing. Should I make a list of the edges or should I make a list of the vertices crossed? Because that's something I'm trying to figure out. Should I make a list of those? Okay. Here's what I have to do. Here's what I'm thinking. Can we have a list of lists? I want to see. Can we have a list of a list of vertexes? Wait, seriously, this is possible. A private. This is going to be for subgraphs. This is what I'm going to call it, subgraphs, and this is equal to a new list of vertices. Oh my gosh, this one is going to, okay, this one is not going to do this. This one is going to be a void, and this one's going to get, this one is, what this one will do is it picks a, this one is going to list, we'll go ahead and get rid of this for now. This one is list subgraphs. Public void list subgraphs. And we actually technically what we can do is we start off by picking a vertex, gedit. Now, all we need to do is to get the first one. And I forgot how to get the first. How do I do that again? Yeah, is it gedit vertices? No, vertices 0? Thank you. Okay, so I think I need to get a reference to, let me look at my notification how I did that. So when we show a notification, info text, it's a list of string. All right, so this is a bit awkward because I have this is a dictionary. All right, so I'm going to need to get item in dictionary. I do not know how to do this yet. The first element in a dictionary without okay, that didn't help. Oh my gosh. Trying to figure out how to do this. Don't tell me I need to do this. What I'm gonna have to do here is make a for each loop. A list of vertices. But wait a minute, how do I? So this one, oh, it has to, you have to add a list. That's an interesting. So first off, I don't know how many. Okay. First off, we just pick any starting vertex. So from that vertex, what we have to do from there is to go along all edges, if possible, and then add starting vertex to a list. at any vertices that are connected to the list. So how am I going to do this? It appears that I have to go somewhere, but then again, I've been live streaming for an hour and yet I barely got anywhere, so I guess I might have to do something. I really want to continue, but let's face it, I'm probably not going to get too far in this episode, so I'm going to have to do some more thinking on my own, and well, yeah, that's really about it for now, so thanks for watching and hope you